Welcome back to day 2. Yesterday we have talked about nonlinear in terms of nonlinear geometry and nonlinear material. So today we are going to focus more on context, right? And most of the time when there is a non-convergence issue or there's some difficulty in convergence, is mainly due to context, especially if you have a lot of context in your model and if it involves large displacement. So yeah, normally those are the things that will cause you some debugging time, right? So why do we need context? Of course, if you don't define context, then parts can actually penetrate each other. So we need context to make sure that they don't penetrate, right? And of course, with contact, you can also have sliding, frictional sliding, and so on, right? Yeah, so several difficulties as mentioned. If there's large changes, means if there's a really large displacement that cause some areas to have contact in the beginning, and then suddenly there isn't any contact. So those type of simulation might cause some difficulties in convergence. Okay, if there's a change in stiffness, suddenly there's a rubber, and then it goes into something like a steel material. So those will cause some difficulty in convergence as well. If it's highly nonlinear, right? If your material is very soft, like for example rubber, those will have some difficulties in convergence. And also if you have thermal conductance. Okay. So basically the contact is defined with this contact card here. Okay, this is what you will see if you open the input deck. Of course, if you open it from the GUI, from HyperWorks itself, it's going to be different. There are a lot, as you see here, there are a lot of items that we can actually define for contact, and we will need to go through all of them because all of them will actually give you different settings to the contact, and some will actually help in the convergence of your nonlinear analysis. Okay, so the basic ones are just your we'll see later that contact can actually be defined 3 ways. You either define it directly by putting in your static friction coefficient, or you can also define it using type. So we'll learn what are the types of contacts. And the other way is to use a property for contact. We call it pcon. Okay, so there are 3 ways to actually define contacts, or defining the settings for the contacts. Okay, then we will need to put in our slave and also our master, right? So what's our slave? This is slave surface ID and then the master surface ID, right? And also, of course, the orientation of your master, because if you're talking about a shell elements can have both sides, right? So you need to define whether which side is actually pointing towards the contacting surface. Then there are some other options available. Search distance. This is gonna generate that contact. You will search based on whatever distance that you've put there. Okay, and then establish that contact at the beginning. So search distance is important. If let's say if your gap is too big and the search distance that you put here is too small, even though you have created the surface saying this is surface 1 will be in contact with surface 2, but if the search distance is too small, then it will not establish that contact as well. Okay. Then we have smooth. Smooth is more for to make your contact contour look better during your post processing. So some areas, especially if you're using the node to surface contact, then the contact contour might be a bit jagged. So if you use smooth here, then it's going to smoothen out. Okay. Of course, then these are the settings for the smoothing. Right. So this is the search distance. Search distance, the way to define, if you don't define search distance, we're going to use automatically. Usually is based on the mesh size of the master surface. So if let's say a master surface is meshed with 5 mm, then the search distance is going to be 5 mm. Okay. But if you want to specifically define that search distance, you need to consider the gap here. Okay. Consider, you don't have to put in the exact gap here. So for example, now this, I have two sheets here, or two shell surface. One is the shell mid plane here, the other is the shell mid plane at the bottom here. Okay. So they are shell elements, but both of them have a thickness of 2 mm. Okay. So when it's projected up and down, you get actually 1 mm here, 1 mm here. So the actual gap between them is actually 3 mm. So as long as you put your search distance to be larger than the actual gap, this is the geometrical gap, which is what you will see in the hyperworks, right? You see just from the shell elements to the next shell elements is 5 mm. But the actual gap, because we have to consider the thickness as well, the actual gap is actually just 3 mm, right? So if you put your search distance to be 3 mm, then we will establish that contact. Okay. If you, of course, even if you put 5, you can still establish that. It's no problem. But you just have to be careful, because if, let's say, this is the actual part here, but let's say if it's assigned, if in the other region is extended like this, okay, where now the actual gap between them is 5 mm, then it will establish contact for this area here as well. So you have to be careful, especially if your part has varying thickness or a non-uniform feature. Okay, that means it is something like this, where there is actually a step. This case, you also establish, if this is 5 mm, the actual gap is 5 mm, you establish that contact as well. But in fact, what all you want to do is actually establish contact in this region only, right? So you have to be careful with search distance. You can put more, but that is only if you are sure that your the thickness is constant, and then all the areas are also in uniform plane, right? Okay, so yeah, so here is just an explanation of how we actually generate the contact, right? For contacts in Optistruct, we actually follow this penalty formulation. Okay, so has the distance between the two slave and master surface becomes smaller, and when it touches, we actually establish that we actually give in a factor here to simulate that contact. Okay, so that's the penalty that we actually put in to simulate that contact. So the more that it penetrates, right? First, the more that it penetrates here, you see the higher the force is going to be, the contact force. Okay. So the higher the penetration, the higher the contact force is going to be. Right. We are using, by default, we're using hard contact here. Okay. Of course, we can actually scale this penalty stiffness. Right? By default, it's going to be hard contact. Means if there's a contact, that means there is going to be contact force that is going to be exerted on both the contacting surfaces, right? But if you are, some of the times you might find that hard contact will actually cause difficulty in convergence, right? It might be difficult to converge with hard contact. You can actually change the stiffness of that penalty here. Okay, so you can actually put it lower. That with that you can actually your slope won't be so steep like this, right? So there will be a slope to it, and you can also adjust the penalty stiffness here. So there are a few ways. One, you can leave it at default, okay, or you can also put it penalty stiffness equals to high or penalty stiffness to low. Okay, so those options are available, or you can also directly put in the value that you want. Okay, so we'll talk about this stiffness later, right? Yeah, so this is the stiffness here is defined under the property for contacts, P-cont, and it's defined under the stiffness here. So you can either put in soft, you can put in hard. Soft means that soft means that it will allow some penetration, some degree of penetration. Okay, hard contact means it will definitely will not penetrate. But then sometimes it might cause some error, some difficulty in convergence. Okay, of course, if you find that both your master and slave surface are having too many or too much penetration, then you can use the hard here. But if you are facing convergence issue, then we recommend to use the soft. Okay, otherwise just use the auto here. Okay, by default we just leave it as auto. Of course, you can also put in your values here. So what are the what scale factor that you want to put in? You can put in. You can manipulate yourself as well, right? Okay. So yeah. So these are the topics that we're going to cover in context. We first learn about type of context, the orientation, the discretization, whether it's node to surface, surface to surface, or node to node. Then we have some advanced features like clearance, move, adjust, and also the track, which is important to determine if, especially if you are using a very large displacement simulation, right? So we go to them one by one. First, we learn about the contact type first. Contact type, as I mentioned earlier, we can define it using three ways, either using type, by putting in the actual static friction coefficient, or by assigning to a pcon. Okay, so we assign the PID 7 here, property ID 7, which actually refers to a pcon card, right? So there are three ways to define your contact, right? And specifically now we are going to look at this type here, right? So for type, you will see that we can actually have three options here. One is sliding, slide contact, sticking contact, and then the other is freeze contact, right? So when you are assigning your contacts to be sliding, it will allow a sliding on the surface, means it's going to be the two parts here are just going to slide, right, along the surface here, but it cannot penetrate, it cannot separate, right? So if you need it separate, you need to define it using the pcon. Okay, so sliding here is going to just allow this one. So this here is not allowed. Okay, of course, with sliding, you can either define it with frictional sliding or non-friction. So you can define your friction there. Sorry, for sliding here, it will be frictionless unless you use this one here. Okay, if you use this and define it, the friction here, then it's going to be friction. Otherwise, here it's going to be frictionless sliding. Okay. Then we have sticking. Sticking means that your part may be separated at first, right? Your part may be separated at first, but during the simulation, there is a force that pushes this block A down onto the surface. And as it touches, then if your contact is sticking, that means it will build after contact is established between them. After there is contact established between them, this part can no longer separate. Okay, this part can no longer separate. So yeah, imagine you can imagine this like there's a glue here that sticks the two parts together. After that, after you have pasted them together, you cannot separate the parts out. Okay, so that's sticking here, right? Then there is a freeze as well. So freeze is you just establish contact at the very beginning, and then it will be bonded throughout the entire simulation. So there's the freeze contact, right? So it'll be contacts will be closed at all times, no matter what's the distance. Here we say no matter what's the distance because even if you have, let's say if your part has a very large gap like this, okay, let's say the gap here is 5 mm, right? 5 mm gap. If you put your search distance here to be 5 mm, we will establish that contact even though you see there's actual gap here. So if your contact is freeze, right? But because your search distance is 5 mm, it will search between the slave and master surface, and you see that okay, this gap is 5 mm, I can establish contact. So it will establish contact even though there's actual gap. So it will be close at all times, and no matter what's the distance between them. Okay, because it's governed by this search distance here. Somebody's coming in. Okay. All right. So yeah, be careful with freeze, especially if your parts are having gap at the beginning. You have to be careful because you will actually establish that contact already. Okay, so just take note of this this freeze together with this search distance here. Right. Similar to freeze, we actually have another contact type which is called tie, or in other words, tie contact. So tie here is similar to freeze. The function or the method or when to use it is the same. When you want to establish a bonded contact from the very beginning throughout the simulation, it cannot separate, then tie and freeze functions the same. Okay. The only difference is tie will actually tie, if you define it tie, we will actually convert it internally to a contact that is similar to freeze contact. Okay, so tie is actually from another solver, is from Abacus. But if you define tie here as well, we actually convert it internally to freeze contact. Right, so it's basically the same thing. But for tie, there's another option to use another type of formulation that is using the MPC constraint. Okay, so that you can define it separately. But functionality wise, it's the same between tie and freeze contact. You are just going to establish a bonded contact between them. Okay. So this load case will help you understand more on the difference between stick, freeze, and slide, right? So imagine subcase 1. Okay, these two beams here, the orange and the purple beam, they are just touching each other. They are not the contact interface between them. We define it using either stick, freeze, or slide. Okay, and then in the subcase 1, in the first subcase, we put a force that is pushing it down. Okay, pushing the orange beam down. Subcase 2 will then introduce a second force in the y direction. Okay, and then the third subcase will be a force. We remove both of these two forces and then introduce a z force that pulls the orange beam up. Okay, so these are the 3 subcases. They're continuous, right? Subcase 1, subcase 2, and subcase 3. Yep. Anything? Right. So if we are using slide, you see, right? Slide when I. Yep. Anything? So for subcase 1, when you push it down, you see, when you push it down, it slides, right? There's a sliding between them, and then subcase 2, you see that you actually push it aside, right? And then subcase 3, when we pull it up, you will actually separate. Okay, so that's a slide. And if you use a stick contact, you'll see that after it has touch, okay, you'll be sticking, and then it will not separate even if it is pushed to the side. But if your separation is on and we pull it up, then it will actually separate. So there's a setting for separation as well. If your separation flag is turned on, you can separate. Okay, but for freeze is a different thing. So is going to be contacting no matter what the force is. Okay. So there's a difference between slide, stick, and then freeze. Okay. So depending on your use case, you might need to use a different type of contacts for different areas. Okay, so we can define frictional, the frictional contact for sliding is defined like this. Okay, as soon as the force exceeds that critical frictional force, then we will actually slide it, right? Yep. So this is mainly used in the sliding. When do we actually start? When does the part actually start to move? It's all depending on the frictional contact that you define, of course. Nothing much to this. We can just this is just theoretical to help you understand the penalty that we actually introduce to sliding. Okay, so it's defined using these two here, right? Where's your static friction and then where is your kinetic, and it's all defined under the P-con cut here, right? So P-con cut, you see under P-con cut there's a separation here as well. Okay, so here well actually, this is just a flag whether separation is allowed or not. Okay. This is just for your information. When we are actually solving any non-linear, we actually use the unsymmetric solver, the mum solver, we call it, right? So you don't have to do anything to this. We actually turn this on automatically. Once we detect that it's a non-linear static, we will actually turn this on. But you have the option to turn this off. You can use this param here to turn it off if you do not want to use the mum solver. But it's on by default, so we just suggest you to just stick to the default. Okay. Right. So of course, there will be difference if there's a frictional contact with and without friction. So this is just to demonstrate the difference. Okay. So depending on whether you need friction or not, of course, in most cases, you definitely need some friction. And in fact, if you introduce a little bit of friction, let's say if even your part, if your part you want to simulate it has a non-friction, but sometimes it might be harder to converge. Okay, so as soon as you introduce a bit of frictional, you introduce a small value of friction coefficient, then it will be easier to converge. Okay, so you can also try that if let's say you're using sliding contact with no friction and you're finding it hard to converge, you might want to just change it to the friction coefficient and then just assign a small value of friction there. Okay. So that's the type of contact. Next, we move on to the orientation, right? So orientation is defined here in this card, in the contact card with this M orient. It defines the which face of the master surface is actually facing that contacting object. Okay, so normally we follow the normal of the elements. We follow the normal of elements. That's why it's normally normal here, but we have the option to do a reverse normal as well. So you can either reverse the orientation of your elements, or you can also reverse this orientation of this M orient here. So you have two options. Either you reverse the element normals or reverse this one. So if you remember, if you let me try to read something in. Let me see if we have some shell elements. Yesterday, I think this one is shell. Okay. Right. So remember your normals. When you check for normals, you can see that. Let me just vector display. Okay. So you remember your normals. Now the element normals are actually pointing downwards. So if I generate the contact later on, it's going to follow the direction of this arrow here. Okay. But if you use, of course, that is if your M origin is norm. But if it's reverse norm, then it's going to be the reverse of the arrow here. Okay. So you need to check your element normals first before you start creating the contact. Okay. Of course, after that, if you see that the contact generated is not in the direction that you want, you can just go to M origin here to either to change it to reverse norm, or you can also do a reverse here. Okay, so either you change the element orientation or you change the contact orientation. Right. Okay. But do take note that for solid elements, the M origin is ignored because we always push out. Okay, so if let's say, for example, a ball, the orientation of the contact is going to be outwards, right? It cannot be inwards. So don't have to worry about if you are using solid elements. Okay, but for shell, yes, you need to take note of this. Okay. Then there are some other special cases where you have an open gap, right? That means there's a gap at the beginning, right? It's initially open, and then there might be overlap as well. So if let's say you want to your surfaces, you didn't solve the penetration, you didn't move the you didn't move the slave surface up, then you probably need to define overlap there to tell that it's actually overlapping, right? So these two are seldom used. Open gap is common, but then normally we also use a normal most of the time, and reverse normal in case your contact or your element orientation is in the reverse. Okay, so just need to define this. By default, it's going to be open gap because we always assume that it's going to be initially open. That's why the search distance is there to help to establish a contact, and the direction will always be pushing towards outwards. Means that the master and the slave will always be like against each other, right? So yeah, you can stick to the default. Of course, if you're using solid elements, then you don't have to be worry about this because solid elements will always be pushing outwards. Okay, so that is the safest. Okay, then we have next we go into discretization. Right, what type of surface, what type of contact is defined for your slave and master? Okay, so the first one defines the first letter here is for the slave side. The second letter here is for after the 2 is for the master side. Okay, so how do you define your slave and master? All right, so yeah, we just have node to surface, surface to surface, node to node, right? If your yeah, there are some defaults here. If you are using freeze contact, there's going to be surface to surface. Okay, if your slave surface is defined with surface, so we will learn later on. There are two two ways to represent any slave surface, either with by selecting the elements to be inside that surface set, or to place all the nodes inside the surface set. So if you place the nodes inside the surface set, then the freeze contact generated will be node to surface. But if you use a set that defines the elements, then it's going to become surface to surface, right? So yeah, basically this is the general rule that we use also lah. If you want node to surface, then of course it's easier to choose all the nodes in the set. If you want surface to surface, that's easier to choose all the elements in the set. Okay. Yep, nothing much here. Yep, there is a difference when you choose surface to surface and node to surface. Sometimes surface to surface is the best because it will give you a smoother contour, right? But node to surface sometimes it's easier to converge, right? So sometimes if you're having difficulty to solve surface to surface contacts, then you might want to switch to node to surface. Okay, you can try this trick here. Right. So this is how we establish that contact. If you use node to surface, each of the node will project downwards to find the master surface. Okay, so that's why it's called node to surface, right? And once it projects down, the projection length and everything is also due to the search distance. As long as the search distance is enough, it can project down and manage to find a master surface. It will establish that contact. We call it that contact element. Okay, we call it element. We call it contact element, but we don't really see it. Okay, we cannot really see it. It's just a formulation that defines the contact between the node and the master surface. All right. Yeah, so it's based on the search distance, so it's important to set your search distance right. If normal projection is not found, then we will also try to find within 30 degrees, right? So sometimes your part might not be parallel. The master surface and the master and slave surface might not be parallel. So we actually can go up to 30 degrees, right? Okay, once the master is found, then we'll establish that contact element. All right. Okay, so this is just some nodes that is internally, right? So if this is just for your knowledge, you don't really have to pay too much attention to it. But for small displacement, we actually convert the contact with a C gap. Then large displacement, we use a different type of element that is different from C gap. So it's just internally what's happening in the background. You don't really need to care about this. Okay. Just know that contacts will work for both small displacement and large displacement as well. Okay. Yeah, nothing much here. Then this is for surface to surface. So surface to surface is the entire surface of the slave is going to be projected downwards and find a master, right? So still it's going to generate 4 because it's still based on the node. Imagine that we still use the node to find the master surface, and then but for one, because this is surface to surface, so we consider all 4 elements, all 4 nodes. That's why there are 4 contact elements here. Okay, so it's like more projection downwards to find, to search for that master surface, right? Yeah, and means that here, as long as let's say if we base on the nodes to project downwards, but as long as one of the nodes project downwards can find it, then we assume that the contact is established. Okay, so even like, let me draw something like this. Let's say if this is the master surface from topwards, top view, this is the master surface. And then if your slave surface is something like this here, okay? But this is surface to surface, right? And because this node project down, you can still find a master surface. So the contact will still be established, right? Even though the rest of this area here cannot find the master, but as long as one of it can find, then because this is surface to surface, it will generate that contact. Okay. Right. So there are some cases where it's seldom used, but just to let you guys know, we also have node-to-node contact, right? Why we seldom use this? Because it will be something like this, right? Node-to-node. We can do this if, let's say, one of the file here, like this shell, green shell, and the RB2 is in one file, and then the C bar is in another file, and then we establish contact between them and read the two files in. Okay, you can do this if let's say you separate your parts out differently. Like for example, the bottom part is stored in one file, and then the top part is stored in another file. Then when you read the files in together, there's a interface file that generates that contact. Okay. Otherwise, normal cases, let's say if everything is in just one file, we just connect them together, right? You don't need to do something like this. But if you want to do something like this, we still have that node-to-node contact. Okay. This will establish that contact between them. All right. Yeah. So it's supported for linear, is supported for non-linear as well, right? Large displacement is supported, but it will not update during the iteration. Okay, it means that you will establish that contact, but then it cannot separate lah, and during the large displacement. Okay. Right. So has CK, you asked earlier, when do you use slave and master, right? So there are some rules or rule of thumb that we follow when we set master and when we determine our master and slave. Okay, I'll go through that. Right, but now let's see this. Before I go to this, let's talk about that. When do you decide slave and master? Okay, so when do you decide slave and master? If let's say you have two objects like this, one is a very small one and one is a very big object. Imagine a table and a ball. So normally the smaller objects will be defined as slave, okay, and the larger objects will be defined as master. Why we do this? Because you might have a lot of slaves, like what you have just now, your PCBs, right? You might have a lot of slaves that is gonna be contact with the PCB board. Okay, so it's easier to define this way because you can reuse that master surface. Okay. Second reason is because it's easier for them to establish contact lah, right? If your slave surface is small, it's easier to find that contact surface, right? To find that master. So having the smaller object has slave is going to be better. Okay. Imagine that if let's say you are using large displacement and the ball here suddenly move to this location, it will still establish that contact, right? So that's the purpose of setting up smaller objects as slave. Okay. That's the first rule of thumb that we follow. Smaller objects defined as slave. Second rule that you can follow is moving object you define as slave. So imagine that, let's say if you have two plates, they are close to each other, but one is static. Okay, one is static, one is moving. Then normally the moving one we define it as slave. Right, the static one will normally be defined as master. Okay, so that's the second rule. And the third rule that you can follow is normally the softer object, we define it as slave. Okay, so softer object, we normally define it as slave. So first, smaller object, second, moving object, third, softer object. Okay, so those are normally your slave, slave surfaces. Okay, but of course, it's not always the case. You can also switch between them. Okay, depending on whether you can get convergence or not, you can also switch between them, slave and master. Okay, imagine that if let's say this is now my static object, but it's actually softer. My E here is lower, right? My Young's modulus here is lower. It's a softer object. My moving object is a harder object. So how do you define this now? Okay, so the rule of thumb is just a general guide. You can actually always switch between them, right? But that's the normal rule that we follow, right? Now that's how do we decide slave and master, and then the next you also might want to learn how do you define node, when do you use node to surface and when do you use surface to surface. Okay, so if you have large sliding problems, then surface to surface is better. Okay, but then surface to surface is, just to let you guys know, it's actually more expensive than node to surface. Okay, it will use more computational time and resource, but you will produce smoother contact pressure. Okay, so if you want smoother contacts, better contour, better contact between them, then surface to surface is the one to use. Okay, if your slave and master surface has a corner, so let's say my object is a box and I'm going to contact into this master surface here. Okay, if there's a corner here, if you use, let me use another color. Let's say I'm using surface to surface, but my surface for the box, I define it in a continuous surface like this. So this entire two sides of the box here, I define it as a single slave set. Okay, when you do this, we have the corner option that you can turn on in the contact card to tell that there's a corner, and then you should consider that this surface here is actually different from this surface. All right, if you're using surface to surface. If you're using node to surface, then there's no problem. Because node to surface is generated based on the nodes, then there's no problem to it. Okay, and sometimes you might find it easier to converge if you use node to surface due to this reason itself. Okay. Besides this corner option, the other option that I normally would prefer, sometimes this corner option will cause some difficulty in convergence as well. So normally what I do is, instead of defining the two sides here as one continuous slave surface, I would normally break them into two. Okay, so I will have something like this. This is my first slave, and this is my second slave. Okay, so I have two slave sets that will actually try to find contact with the master surface here. Okay, so this is a better way to determine to establish contact rather than having, if it involves a sharp corner like this. Even if, let's say, if your corner is not sharp, you might have something that is varying like this. Okay, I will also break them into two different contacts. Okay, I will also break them into two different contacts. One I put it here, the other one I start it from here. Okay. Okay. So some guide on when to use node to surface and then surface to surface as well, and then what's the default. So you can follow this table as well to see. Basically, surface to surface is supported for all types. So there's unless there's convergence issue, then you probably want to switch to node to surface. Preferably, I like to use surface to surface because it gives me a smoother contact pressure between them, right? So yeah, normally use surface to surface. So if we see here, oh yeah, there's another rule. Forgot another rule, the fourth rule of when do you choose your slave and master. Normally, if your mesh size is bigger, that will be your master. If your mesh size is smaller, that will be your slave. Because you want your slave, the smaller mesh size, to fall within the master surface, right? So yeah, so it's the same rule. So if your part is smaller, if your mesh size is so smaller, then that will normally be your slave. Bigger one will normally be master. Okay, so for this example here, let's check what's the difference between node to surface and surface to surface. Now the bottom is slave, so smaller mesh size is slave, bigger mesh size is the master. They're both objects are same size, right? And then we have enforced displacement that's pushing downwards. Okay, so you see now actually the moving object is actually the considered master here, right? Now if you use node to now let me just track back a bit. So now remember our rule, the smaller mesh size is gonna be slave, bigger mesh size is gonna be master. So that is following the rule of thumb that we set, right? And because of this rule of thumb, you will see that the stress contour here is actually pretty okay. Even for node to surface, right? Node to surface, the stress contour is still pretty okay. Okay, of course, it's not exactly what we want, for example, in surface to surface, because it's definitely a better contour. Okay, here we see that there's some discontinuous, right? Okay, so node to surface will give you this kind of results. Okay, it may not be a smooth contour, right? But if you reverse it, if let's say now the bottom is slave and the top is master, okay, then that will actually violate our rule, right? Our rule states that the smaller mesh size is slave, but now we use the bigger mesh size as slave. So when we reverse that, when we reverse the condition, you see that now the node to surface, you see there is like jagged. Some areas will have contact, some areas doesn't have contact, right? So, but if you use surface to surface, it's still generally okay. All of the elements are still like being pushed down together. But now some areas that see here, there's, let me see if I can zoom in. So you can see here, some of the areas are not in contact. Those the orange ones are in contact, and those not in contact, you see they're actually not being pushed down. Okay, so so here is that if you use surface to surface, even though your master and slave definition is the other way around, you didn't follow the rule of thumb, you can still get a fairly reasonable result. So all the nodes are still being pushed down, all the surface are still being pushed down. But here, if you use node to surface, then you see this jagged condition already. Okay, because some of the nodes didn't manage to find a master surface, so that's why it didn't have any contact. Right. So if you follow the rule of thumb, you are generally going to be safe, even though if you use the wrong discretization here. But of course, that's why I always stick to surface, right? No matter if my rule here I follow or not, I would generally have a better contact pressure, more distributed contact pressure. Okay. So no matter what's the condition, if your master slave are defined correctly or not, you still get a smoother contour with surface to surface. Right? So that's why I always recommend surface to surface. Okay. So imagine just now your question, you have a shell element. You're going to generate contact for both top and bottom, right? So imagine this, I generate a contact now. I create a set segment. Okay, so don't ask why we call this set segment. Alright, it should be called surface. Right, so if you need to create a contact surface, you right click, create set segments, right? We also have actually another button here, this new under model, there's contact here, but I prefer to use this. Previous version still got bug like in 2020. So just right click, create set segments, and then normally I would, let's say I call this master one, right? And then I select my elements. Oh, I didn't show you this also. So, yep. So you need to check your element normals. Okay. So you have to see whether your elements are pointing upwards or pointing downwards, right? So if I display here, now these element normals, they're all pointing downwards. Okay. So you need to after you mesh, especially for shared elements, you always need to check this. Make sure the element normals are all synchronized, right? If you have certain areas that are in the opposite direction, all you need to do is just hit on adjust here to adjust it back. So for example, let me show you if let's say right. So if let's say some of the elements like this, right? When you mesh, sometimes the elements created are like this, right? They are not in the synchronized normals, right? So we need to synchronize them back. All you need to do is just hit on this adjust here and it will adjust it back. Okay, so once this is adjust back, now if I create a contact, it's going to follow the normals here, which is going to point downwards. Okay, so now if I create a element here, right, and select the face and click add, now you see the contacts created are following the normals of the element. They're all downwards, right? Now this is contact that is from this side here. If you want to have contact on this side as well, you will need to create another surface here, right? So let's say now this is surface 2, right? And of course you can choose the same elements, but here you check reverse normals, right? Add this, and now you see the contact is on the other side, right? So you need to do this for shell if your shell has contact on both sides, right? Then of course when you define contact later, one is going to use this master, the other one is going to use this master here. Okay. So that's for shell, right? Right. So here I'm going to teach you how to use this auto contact. So as you seen, normally for Optistruct contact we define in pair lah. So we define the master and slave, right? But if let's say you want to just automatically have Hyperworks to search the contact for you and define it, you can try this button here. It doesn't, I'm not sure if it works, it will work all of the time, but you can use this if you are too lazy to search, right? So under model, there's this contact here, right? You click on this lightning button, auto contact, right? So just click on that, feed in the components. I'm going to select the 2 components, okay? And then we put in the tolerance here. So the what's the gap proximity gap, okay? So you can put any value here so that you can manage to search and establish that contact surface, okay? What contact type you going to use? Is it going to be sliding? Is it going to be tight? So let's say it is sliding. Then you have seen some other options as well that you can put in, right? This is more for the search distance, okay? And then we're gonna establish contact here. This is the set. So there are two ways to generate sets. One is either you use a set, or the other one is we call surface. Okay. Now the name is a bit misleading. If you choose surface, it's gonna actually create that set, right? If you choose segment, it's gonna actually create that surface, right? So don't be confused with this. Just stick with whatever it is. We can change it later on. Okay. It doesn't matter if your contacts are established, are created using sets or segments, right? So if you right click here, you see there's a set, and then there's a set segment. Set segment here refers to surface. Set here just refers to set. Okay, there are two ways to create that stave surface or master surface. Either you use set or use set segment. That's all, right? So this one is corresponding to that, right? So don't worry, just use the segment here. It's fine. We are using sliding because sliding here is turned on. If you want to choose another property, then you can choose here. Okay. Don't worry about this also because we can also change this later on. Okay. But if you want to have everything done in this toolbar here, then you need to put this correctly, right? Otherwise, otherwise you can also tweak it later on. Okay, so don't worry. Here, most important is we want to automatically create that slave surface and the master surface. Okay, so using sliding, choose the component and then say fine, right? So it automatically search, and it manages just that these two are two different parts. That's why it only establish contact in between them. So you can see this is the contact that is generated. Right, so this is the contact that's generated, right? So if you go to the sets here, you see it has created the segments, right? So this is the bottom surface, right? And then this is the top surface, right? And how do they establish the contact? If you go in the contact here, you see it uses the type sliding because we chose sliding just now, right? And then if you see here, the master and slave, the top. Let me just exit this, confirm this first, right? So exit that, and you see the top, the slave is bottom surface. So this one here, the bottom surface, let me just remove this. All right, so bottom surface, okay, is the slave, right? And then the top surface is the master, and is using surface to surface, right? So you can still tweak this if you do not want. If you want to change any of these, you can still tweak. Let's say if I want to introduce some friction, I can just change this to static friction coefficient, put in my friction here if I want. Okay. Now let's just stick to slide first, right? And that's it. Unless you have further options like what's the search distance and so on. Otherwise, this is actually good to go. Right, this context already established. We can actually use this now. Okay, so that's the auto contact. You can try this. After that, we can set this up for a non-linear run. So let me see if the SPC is already defined. Okay, SPC is already defined. Some are constraints, some are enforced displacement. So this is in the direction of 3, is actually pushing it down. You can double check on this, click on the loads. Right, so it's actually -5 is pushing downwards 5 mm. Right, so all this top is going to push downwards 5 mm. Okay. And we also have an NL pump that's already turned on, but it doesn't have anything yet. So let's put in a DT here, initial time step of 0.1. Of course, if you want to have NL out as well, that would be good. Right. NL out. Let's choose, say, 10 increment. Sorry, 10 outputs. And then what else do we need? Let's try without now adapt another first. And then you can just create that little step. Okay. So change this to non-linear static. For SPC, just put in the SPC that we have. Okay. There's no loading because the enforced displacement is defined using SPC. So it's also grouped under SPC. Right. So you can just use them all. Then NL palm, I'll just choose large displacement because -5 is quite a large displacement there. Right. NL out. Okay. And let me choose a monitor as well. So I want to monitor the displacement. So to track, see whether the simulation is going all right. So I probably want to track one of these nodes here. It's in a middle node. Okay. Right. So in my monitor file later on, it's going to print the displacement of this node at every iteration. Okay. So it's going to be tracking the third component, the Z displacement, right? So that's the monitor. Okay, the rest are okay. Then let's choose some outputs, right? So let's go and activate global output requests. Okay. Of course, the displacement, stress, strain orders are the basic, right? Oops. Stress and strain. You might want to look at reaction forces if you want, just turn that on. But most important, if you're doing context, the best thing to have is actually this, to turn this on here, contact force. Okay, so turn on contact force, then you get to see your contact pressure, your contact, whether there's contact or not that's going on, right? So when dealing with contacts, to make sure that your contact is always okay, always turn on this one, right? Contact force. Okay, and yeah, so you see the cards here created. The rest, I don't think we have anything else. Flash display is already turned on. Yeah, so the rest are okay. We can try to run this now, right? So try to run this. Just rename this as different name. And this is upscale engineer. Yep. So I'll just run this now. Okay. Something's running on my background. Okay. Yep. So it's gonna solve pretty quick. See from the folder here, it's done. You look at the monitor file. You can see that it always tracks this grid here, right? So this is the ID that you have chosen in the monitor. So always track this. You know that what's the progress of your simulation, right? Because of the adaptive time increment that we adopt, so you can see that even though we request for 10 outputs, we won't get 10 outputs, right? So even the number of intervals in here, NL out, NINT 10, right? We might not get 10 because because of the adaptive time increment. As long as he detects that it is actually easier to converge, it will actually increase the time step. Okay, so that's why if you want specific time steps to output, better to use time here. Okay, otherwise it can be smaller than it will have fewer outputs, right? So as you can see, the increment actually increased a lot because it finds that it's easier to converge. All right. So let's look at the results. And it should Let's look at the out file as well. It should be solved without error lah. Here. Yep. So let's look at the results. Okay, so we need to have all this. Yep, so we have 10 outputs, but then it won't be exactly at 3 and then at 4 and 5 and 6. I don't think we have 10. 2, 3, 4, 5, 6. Yeah, we only have 6 outputs here. So even though we set the NL out to have 10 intervals, we might not get 10 intervals. Okay, so we can always look at contact force when we are looking at forces at contacts. Okay, so this will give us a better idea on whether we generate the contact or not. Too fast. Okay, so let's remove one of the blocks. See contact established. You can also look at contact pressure to see contact force. Yeah, contact force. Right. So you can see the pressure distribution. Now this is surface to surface. If the smaller mesh size is going to be slave, right? So this is like the ideal condition. Okay, yep, so that's the best case scenario where we have smaller mesh size as slave, and then it's surface to surface, right? So you can also try and change that to node to surface. You can also try another run. See what happens if you get node to if you use node to surface. It's 2S, right? You can try to change this to node to surface, right? See what happens. Right, and you can also reverse the master and slave. To surface, let's say, you can also try to reverse under context, right? Reverse this one here. Instead now this is 2 and then this is 1. So you reverse the master and slave. Okay. I can save this as another one. Okay. Right, so you can try that and run and see what happens. And then for this one, you can also open. And let's say now I try surface to surface, right? So you can run this and see what are the effects of changing those surface to surface and also changing that master and slave reverse, right? Okay. So you can try that. I will not go through those examples. Where's my slide? Okay. All right. So yeah, try to use auto contact. Otherwise, you can also use the manual way to create, right? Now, yeah. So this is the example. Say to node to surface or surface to surface example. Then I'll move on to the next, which is adjust, right? So advanced features here: clearance, smooth, and adjust. Adjust, you can use adjust if you have initial penetration. Okay, so adjust is going to help you, as the name suggests, adjust back your position. Okay, if there's a small gap you want to adjust also, you can also use adjust. Means that the two surfaces supposed to be in contact from the very beginning, but your actual mesh doesn't have contact with each other. Means after you've meshed the parts, there's actually gap, but you want to move you can either manually move the nodes back to touching condition, or you can use adjust to shift those nodes as well. Okay, the good thing about adjust is as we move those nodes, we do not cause any strain to the model. So there is no like initial strain generated when you use adjust. Okay. All right. So here is an example of adjust. You can set adjust equals to 0. If adjust equals to 0, we will search if there's any nodes that are in penetration, we will move it back up. Okay, that's it. Right. So if there's any initial penetration, we will move those nodes back up to touching condition. Okay, so that's and this is gonna be strain free. That means there's no initial strain. Okay, moving back up won't cause any additional stress here. Right, these are zero strain here. Right. But do take note, if you use different discretization, if you use node to surface, then you see the actual nodes being moved. But if you use surface to surface, the nodes location are not changed. Okay, but we just take into account that there's no penetration in the beginning. Okay, so adjustment is just adjusted as a change in the initial contact. That means there is no penetration at the beginning, but the location of the nodes won't be actually move up. Okay, that's if you use surface to surface. Okay. Now, if you use adjust larger than 0, if you didn't use adjust equals to 0, but you put a larger value here, say 1, we are going to search for both top and for both gaps and penetration. So for example here, let's imagine that we put adjust equals it just equals to 5, for example. So you will search 5 mm up and 5 mm down. You manage to search that all these grids here are penetrating. All these grids here are there's a gap. So you search all these and you position them back to touching condition. Okay, so that's if you use adjust equals to a certain real value. All right. Yeah. So another example here of when if we use adjust equals to 0, there's initial penetration here, and then there's an initial gap here. If you use adjust equals to 0, we will adjust back those that are penetrating. Okay. If you use adjust equals to a real value that's larger than 0, then we are going to adjust both both gaps and both penetration. Okay, so yeah, this is done in the initial. There's no additional strain caused during this adjustment. Okay, so this is adjust, and this if it's node to surface, right? We can see this physical movement. But if you use surface to surface, you won't see this physical movement. We just make sure that initially there's no penetration and there's no gap, right? Right. So yeah, so just take note, if it's node to surface, it's going to be initial change in the model geometry and also adjustment of the grids can be visualized, right? So surface to surface is just going to be treated as just a change. There will be no visualization of the adjustment. Okay. You can also specify adjust to be auto. If you use adjust equals to auto, then we actually use a 5% of the master element size. Okay, so if your master element size is, let's say 10 mm, we will take 5%, which is 0.5. Right. So yeah. You can use auto as well. Right. If you want to output, if you want to, let's say you have done adjust and you want to get the final output, or you want to get a copy of this adjusted nodes here, you can set this contact param, con param, right? If you use this con param, we will actually print out a bulk data file. So you'll get a .fem of this adjusted script here, and then you can use this for the next run if you want. Okay, so that like we automatically fix from here towards here, and then output you that file. Okay, this is using this con param here. Right. Right. So this is an example of adjust. Of course, you know adjust. You see there's initial penetration at these areas here. Okay. So once it's adjusted, then you see it's better now. Right. So there's no initial gap or initial penetration. Right. Right. So let me show you adjust. Okay. So you see here there's initial penetration, there's initial gap. All right. So you can use the contact here is already established. All you need to do is just go and manipulate this adjust here. Okay. So you can either use a string value, you can either choose auto or no. Auto will just based on remember the master and then the master size, the size here. So let's say, let's just measure this size is about 1.67, 5% of this, okay, will be treated as the value for adjust. Or you can also set your own values here, change this to real value, and then you put in your distance to search here. If it's 0, then we are just going to solve all this penetration. The gap here won't be solved. If you want to fix the gap as well, you might want to estimate this gap here. Okay, so let's just put this as the entire size is 1.67, so probably won't be that much. So I just put adjust 1 here. Okay, so this will fix both gap and both penetration. Okay. Yep. So only node to surface will get to see this movement here. All right. So if you want to have the con param at adjust grid here as well, we are gonna output that bulk data file for you. After we have moved it, we will actually save that file as a copy for you to use for the next run. Right. So it's con param here. Right, so let's try and run this. Load step should be already set. Okay. Let's check on the loads. Okay, put SPC inside here. Okay, so let's try to run this. Now we've adjusted already. What was this? Adjust equals to 1.0, right? because there's no NL out. So if there's no NL out, you can manage to solve in one step, you will solve in one step. And because n param also is 0, so you will solve in one step. Rather not do that, let me just do some time step here. Okay, so I'll override it. Okay. So let's look at the results. Right, so you see we have the files created as well. Those that have already fixed, we have fixed it and saved a copy of it, right? So we see that we have saved a copy of the FEM file also. So you need to just open that. So it's just the grids, right? So you need to overwrite the existing grids in your original file. So you can do that by reading it here. So let me try to read this. Now this is the original file where there's gap and penetration, right? I will read that, import solver deck. This one here. And when you open this, important that you go to ID offset and say overwrite here. So this will overwrite the grids. And this is the safe one, right? This is the final one that is yes fixed. Okay, so important when you read it in, you need to overwrite it. This will actually overwrite the grids here onto the original file. Right. Let's look at that file now. So you see this is the one that's fixed. That was okay. Yeah. Okay, so the initial step you see that it has fixed all the gap and penetration. Right. Yeah, because I don't have NL out, so you need output the final step for me. So important, if you're solving nonlinear, try to have NL palm and also NL out together. Okay, so you need to create NL out as well. Okay, so yeah, that's the adjust. Any questions on adjust? Okay, so you can try different values. I put adjust 1 just now. You can try adjust auto, and if you don't have any adjust, what will happen? Okay. Now the next advanced feature is clearance. Clearance is to set that contact, right? Initial contact, irrespective of what the actual geometry is. So in the actual geometry, there may be a gap, but if you set clearance equals to 0, means that it's already in contact. So it will disregard the actual gap and establish that contact already, right? So you can use clearance equals to negative as well. If it's a negative clearance, that means you have a interference fit, right? So that means there's a fit there already, especially if you're doing bushing and so on. You can use a negative clearance. Okay. So important to note, clearance will override the initial gap. So no matter if, let's say your gap here, let's say this is my part, I have another part here. Initial gap here might be 5. if I set clearance equals to 3, that means now the gap has turned into 3. No matter what the actual gap is, the initial gap I have here, clearance 3, then the contact will be established. If this part has moved by 3 mm, then there's already contact, even though my contact here I set to be 5. Right? Don't confuse this with search distance. This is search distance is to check the beginning, right? The beginning whether there's a contact or not. So yeah, there are two different things: search distance and clearance. Okay. Right. So that's positive clearance. Then you have negative clearance as well. Okay. So negative clearance is normally for interference fit or press fit. Right. Yeah. So don't confuse with search distance. Search distance is contact surface, right? Clearance is a different thing. Okay. So yeah. So example here, if the gap here is a gap of 0.1 mm, if I set clearance equals to 0, means there's already touching with each other at the beginning. Okay, so this one will have, you see there's a contact force here. Okay, if you set clearance equals to 0.07, you will move, means this has to move because the initial gap or the geometry gap is 0.1. It has to move 0.03 before it establish that contact, because these two add up together equals to 0.1, right? Okay, so yeah, clearance will override whatever gap that we have at the beginning. Okay, and of course, if you put a negative clearance, then you're gonna have an interference fit, right? So you can see here that there's already contact established because it's like pushing each other. Okay. Yeah. So for clearance, you can set it from here. I'm not going to use this example, but I'm just show you how to set it up. For example, here, right? So if you want to set clearance, all I need to do is, let me try to just move this. Let's put, okay. So let's say if there's a gap here, right? If I want to move, if I want to set a clearance, let's say initially geometry has this gap, but I want it to be touching already. So I set my clearance equal to 0. Okay, so to do that, you can go to contacts and then find this clearance here. So I put clearance equal to 0, means that you will already have contact at the beginning. Okay, if not, let's say I put 0.05, you'll move halfway downwards before it generates that contact. All right. So yeah, you can try this also. Adjust here is okay, so let me put adjust 0, or choose no here. Okay. So let's try this one. I would save this as a separate file first. Right, it's done. Let me read the file in. Clearance. Okay. So my clearance value was 0.05. The gap was 0.1. Okay. So let's try and look at the contact force. Wait. context already established at the beginning because I don't have my track. Okay, so I'll rerun this. Right, we'll learn about track later. So track will actually update the contact definition at each iteration. Okay. Read the file in just clearance. Oh, sorry, solve as static. Okay, I need to create the inner out cut. Yep, so important to have inner out for nonlinear runs, otherwise it's going to just solve as a static. 10 iterations here. Need to define it here as inner out. Okay. Let me close this first. Right, so now we have inner out. Okay. Now you see now at the beginning there's no contact force because there's a gap of 0.1, but my clearance is 0.05. So as it moves to the next step, then even though you see geometry wise there's still gap, but the contact has been established because of the clearance, right? Clearance is smaller than the actual gap. Be easier to turn this. Yeah. Okay, so now there's contact already, and now you see the contact has been established. The gap is always going to be constant because in the simulation wise, it's already have contact already due to the clearance. Okay. So yeah. Hope clearance is clear. All right. Okay. Stop this. Okay, so let's go. So you can try clearance with the block is now. You can try clearance with this this file. Okay. And then the other advanced feature is smoothing. So smoothing will, as the name suggests, just smooth the contour. Okay, especially if you have if you're using node to surface, or if you're using you have a lot of angles like this. Okay, so smoothing is gonna help you. Okay, this is mainly just distribution of the contact force, right? Yeah, it only applies to surface to surface. Yeah, so condition here does not apply to freeze contact. Okay, you can apply it to adjust and clearance. So Yeah, if the surface to surface discretization doesn't give you already that smooth enough contour, you can turn on smoothing, and then you can just choose to smooth which side, whether to smooth at the master side or smooth at the slave side. Okay. So example of smoothing is something like this, where you get a smoother, more distributed contact force. Right here as well. So this is contact tracking, right? There are three options here: small, finite, and continuous. Okay, so for if you didn't set the track, by default it's going to be small, and small tracking means that the contact is established at the beginning of the step, and then it doesn't get updated throughout the simulation. Means if on the step time equal to 0, it found the contact, it established the contact, and it doesn't get updated. Means throughout the simulation you have that contact. Okay, even if let's say the force is large enough to separate the parts, the contact will still be there. So that's small. Okay, when do you use it? Basically, when you estimate that there will be a little bit, very small movement between your master and slave, which is less than 1 element size. So if that's the case, then you can afford to use small tracking here. Okay. Then contact update is only at the load step, means at the beginning of load step. Let's say if you have 2 to 3 load steps, it's gonna generate the contact at the load step, and it doesn't get changed throughout the loading increment. Okay, so it stays the same, right? Of course, with this contact that doesn't get updated, the computing power will be lesser, so it's going to solve faster. And it doesn't actually solve for large displacement. So here's where we assume that the displacement is going to be small. So large displacement, if you need large displacement, this small tracking will not be relevant really, right? Because if you are expecting a really large displacement. So if you're talking about large displacement simulation, you need to go for finite, right? So for finite tracking, your contact can change, means that the contact area can shift from one region to another region, right? So it's going to get updated every load increment. Every time step you get updated, okay? And of course, with this updating in contact, it'll be higher computing power, right? The most expensive computing power is in continuous sliding, constantly here, right? Continuous sliding. So here it's if let's say you need to get it updated every iteration, okay? What it means is this. If I were to open an out file, okay, so for example, this out file here, right? So if I am using track equals to small, means that the contact will remain the same for all increments, okay? If I use track equals to finite, the contact will get updated every increment, okay? So increment 1 you check for contact, establish that, okay, solve it. Increment 2, then you check for contact again. Okay, so certain areas might have contact, certain areas might not have contact already. So you checks again, update the contact, and then solve it. Okay, same goes on to increment 3 and so on, right? But for continuous sliding, the contact gets updated every iteration here. So iteration 1, it checks for contact, solve it. If it doesn't, if it violates that convergence criteria check, it will go to a second iteration. It will then update the contact again. Okay, so contact, certain areas might be closed, certain area might be open. Means that the contact might be on or off. Okay, and then for each iteration, you do that update. So that's why it's more. It requires more computing power because it updates the contact, it searches and then establishes the contact for every iteration. Okay, so that's why it's more expensive. So that's the 3 level of contact. When do you use When do you use them? Of course, when you're talking about small sliding, you can just use small. But if you have a large displacement, then you have to either choose finite or continuous sliding. You can choose continuous sliding if there is a huge difference. Let's say the convergence issue is very large, you cannot solve it, then you can choose to go for continuous sliding because it upstate the contact. And let's say you have a lot of penetration, the contact is not established correctly. Some of the nodes on the slave get sticky, right? Like the surrounding areas, the contacts are off, but only one point the contact is still on, and it's kind of sticking to the master surface. Those are the issues that you can face sometime, and you need to update it every iteration. So you go for continuous sliding. Okay. Otherwise, finite should be enough. So I will normally base my contact on whether I am doing large displacement or not. If large displacement, I'll go for finite. And if I run finite and I see that a lot of slaves are still like sticking to the master, even though it's far away, then I probably want to turn on continuous sliding. Or if my contact is there are a lot of penetration, right? There's still a lot of penetration there. I can also try continuous sliding. Okay, so this is the most expensive because it updates every iteration, right? Right. So if you want to have self contact, we also have self contact in Optistruct here. Means that the master and slave are actually the same part. So for example, the best example would be a G clamp. Let me just draw that. So the best example would be like something like a G clamp. Okay. All right. So they are both the same part. You can establish. The other way to do this is to generate a different contact for master and slave. But if let's say you choose the entire surface here has one contact surface, okay, then you can use self contact as well. So for both master and slave, okay, let me choose a different color. Probably is better. One way, what I normally would do, I will assign this as master, okay, and then assign another contact surface here. Another contact surface here has slave. Okay, this is the best to do. But if let's say you want to have a single definition of contact surface for the entire face here, right? You can also do so. If you do this, then you need to establish that self contact. Okay, so for self contact, you need to turn on continuous sliding, right? You can use either one, either node to surface or surface to surface. Another example is your spring. So if let's say your coil spring, right? If you just select the entire face, it's going to select everything. So the entire face that you select is going to be your contact surface. So you only have one contact surface. If that's the case, then both your slave and master slave ID and master ID will be the same. And then for tracking, you need to turn on continuous sliding. And of course, the discretization can either use nodes or surface is fine. All right. Yep. So here for self contact, you can either put master ID to be blank, or normally I'll choose them to be the same. So I know that I'm using self contact. Right. It's easier for me to see from the input deck later on. I have under the contact, you have both the same ID here. Okay. Right. So that's self contact. Yeah. So here's an example of self contact where actually this is crushing down. So you see this crush here, right? So if you want self contact, because the inner part, inner surface here is one contact surface, outer is one contact surface, and as it crumbles, it has the possibility to contact with the bottom part, right, or with another layer. So you see here, this way you can establish a self contact here. Of course, here you need two contacts, one for the outer surface, one for the inner surface, right? But at their respective cards, both the slave and the master is going to be the same ID. right? And you need to turn on continuous sliding. So needless to say here also you see it's actually large displacement turned on as well. Okay. Yep, here's an example of finite. Here, this can be finite, this can be continuous sliding, so it's up to you. If you can solve this with finite, then you don't need to go to the more expensive continuous sliding. Okay, of course, here also you will require large displacement here. All right. Now we go to some contact outputs. As we have learned earlier, one of the most important contact output is actually the conf. Okay. The conf there, right? And when you actually request for conf, basically you get all these options here, force, and then the all these deformation status, whether it's on or off, open or closed or frozen, right? If you want to look at pressure, you need to define it through Pcon. So if your contact is not defined through Pcon, you just use the type, either sliding, freeze, or stick. Then you get contact force. If you want a pressure, right? If you want to look at pressure, contact pressure, then you have to use a Pcon definition, right? So if you use the friction, if you have friction on, then you see this also, these results also, right? Yeah. So this is an example of the contact status, right? So for contact status is because you can either have, actually it's a discrete result, right? You either have open, closed, or frozen. But to make it visible in hyperview later on, because we use the legend, right? And a legend is basically a continuous legend. So we have the denomination of 0 for open, 1 for closed, and then 2 for frozen. So even though you see it's a continuous value here on the legend bar here, but you get to know that 0 means that 0 here means that is open. Okay, if you have the value of 1, which is basically red color, right? Red color here, that means this is closed. So contact is established here. If you see a 2, that means it's frozen, right? Same goes to the output for slip and stick. Okay, especially if you have kinematic friction, then you can see this as well. So this we convert the discrete values or discrete results into continuous values here. Okay. Right, and we will learn later on that we can actually apply a energy called contact stabilized energy, contact stabilization energy. Contact STB. Okay, contact stabilization CNT STB, contact stabilized energy. Okay, so when similar to the static stabilization energy, the contact stabilization energy will stabilize the model when you have contacts in the model. Okay, so of course with introduction of external energy, contact stabilized energy is the external energy. When we introduce to the model, we have to make sure that at the end, the energy is very much lower than the strain energy of the model. So by a general rule, also is 10%, right? Similar to the static stabilized energy. As long as the energy introduced is less than 10% of your strain energy, then the model is okay, right? The results in the model can be trusted, okay? So this is the same. We print this under the ENLM file, which you can also load through the energy MVW. So let me show you one of it. So we see here something that we ran yesterday, you see something like energy MVW. So you double click on this and this will plot this plot for you. You plot this energy plot for you. Okay, then you can have a look and see whether your contact stabilized and also your static stabilized energy is below your strain energy. Now, yesterday we didn't use any contact stabilize, so whenever I plot any of this, it doesn't really have that. It doesn't really have that that contact stabilize. Okay, so as long as you don't turn on static stabilize, it won't actually print that static stabilize. If you didn't use contact stabilize, also you won't print out that contact stabilize because there's basically zero lah, right? So far we have not used any contact stabilize, so we don't see anything of that on that. But we have used some static stabilized energy yesterday in the stabilization run of the buckling. So those we get to see the energies there. Okay. Right. So it's actually very important to compare this one so that you know that your results at the end can be trusted. Okay. Sometimes you might want to look at the contact that's being established. So contacts are just formulation. We don't really have the element representation of it. Okay, but if you want to view them, you can still do so. Right? If there are certain areas that cannot establish contact, we'll actually print out a .fem file that tells you that there is no contact established. Right? Contact fail to establish in these areas here. So there'll be the grid numbers, or we actually categorize them into sets, and then you can read in the sets into your HyperWorks and check where are the areas that doesn't have contact. Okay, so there's a separate file. It will only be generated. It's going to be generated automatically, and it will only be generated if it finds that certain area doesn't have contact. Like for example, if your slave area is this big and only part of here gets to generate contact, we place all these grids here, or all the elements or all the grids under a set that is going to be stored under this here, under .fem. Forgot the name. It's going to be something like no consem. So far, we don't have anything on that. Later, we can see if we have example on that, right? So the name will be obvious. There's it's going to say like something no contact .fem, something like that. Okay. Right. So that is for areas that didn't manage to generate any contact. Then for those areas that you have contacts already, if you want to view them in the HyperWorks, you can request for this output here. Okay, so you can request for this contact param, con gap output, right? Two methods. You can either use a con gap or con out. Okay, so con gap is only used for node to surface, and it will represent those areas that has contact has C gap elements. So you can see something like this, right? So we will generate something like this to denote that there is contact. We don't actually use this C gap element for contact. It's just a representation, right? And if you use the con out option here, we are going to represent it with this RBE3 plotel. So it's RBE3 and then RBE3 at the bottom and then plotel in the middle. Okay, so yeah, RBE3 plotel here. Plotel is just plot element. All right. So again, this element is used to just represent them, represent the contact. It doesn't really use it for contact calculation. All right. So yeah, just take note, you can actually turn this on if you want to view contact. All right. Okay. Right. So here is the stabilization energy that you can introduce to stabilize your run, and then of course when your run is stabilized, you get to converge, right? So if the model is experiencing a lot of instability because due to the context, you can introduce this context stabilized cut. Okay, so there are also a few ways to generate that context stabilized, right? One is to use that cut in specific. You define the cut here, right? Once it's defined, it's going to be used. The other option is to use a param expert NL. So I talked a bit yesterday. There's a param expert NL where we apply yes. Okay, if you apply yes, it just adopt that time time increment adaptation. Okay, if you turn it to contact stabilize here, it will activate this contact stabilized energy. Okay, so yeah, once you have this contact stabilization energy turned on, it will print out the energy that's introduced in this file here, e.nrm, and of course later on you can use the session file to plot it, so you get to see something like this, right? As long as the contact stabilized energy that's introduced is less than 10% of the strain energy, then it's okay, right? So the highest is here, strain energy, so it's actually definitely less than that, right? So this is the contact stabilized card. Most important thing for this card is first you need to know the keyword, and the ID will take care of itself. The only thing that you probably might want to manipulate is the S0 and S1. So this is a scale factor for the stabilization energy at the beginning of the subcase and at the end of the subcase, right? So your run might get unstable maybe in the beginning. So that's where you want to put a factor of 1. So that's why I put a factor here. So if the stabilization energy were to be introduced, it's going to apply this full factor here, right? Factor of 1. Otherwise, at the end of the run, we want to make sure that the energy is being removed. Okay, so at the end of the run, probably you want to set it to be 0, or if it is still unstable at the end of the run, you can use a very small value, 0.01, for example. Okay. So yeah, the only thing that probably you might want to manipulate is just this S0 and S1, right? Okay, so yeah, so there's contact stabilize. Then we have preloading here. So we touched a bit on preloading yesterday. Here's an example of how we can refer a new subcase to a NL stat, okay, by using this stat sub here. Of course, we learned yesterday there are other methods. You can use the continue nonlinear sub, right? CNT NL sub. So you can use that also, or you can also use a stat sub here, right? Yeah, so same yesterday. Okay, preloading support, we have both discretization, so no problem, with and without friction. Okay, you can use stat sub. Stat sub again will just update the stiffness. Okay, if you want to update the conditions as well, you want the stress, displacement, and strain to carry over, you should use the continue nonlinear sub. Okay. So yeah, stat sub can be used to refer to linear or non-linear static, whether it's small, large displacement, contact, and so on. Right. So example of use case is something like this. First, you might have a large displacement. Maybe like here, there's a large displacement here, and your stat, and then you use then there's also pre-tension here, and then you use the result here and carry over the stiffness result that's calculated from subcase 1, carry over to subcase 2. Right. So subcase 2 here is a method, so it's calculating for the normal modes analysis, right? But they might have a pre-tension at the beginning and use the pre-tension to simulate for the normal modes, right? Example is like, if let's say I have 2 plates here, right? And I have a bolt, okay? It's bolted, right? Now, there will be a lot of difference whether I pre-tension this or not. So that's why there's pre-tension applied here before we run a normal mode analysis. Without pre-tension, maybe the two, there won't be any stiff connection between the 2 plates here. Okay. Once there's pre-tension, then you'll be like clamped together. All right. So that's why it's important to consider pre-tension, especially if you have bolts, before you run for a normal mode analysis. Running that with and without pre-tension will be different. We also have fast contact in Optistruct. So fast contact is an alternative formulation, right? Compared to what we have learned earlier, right? It's going to be, as the name suggests, it's going to be faster, okay? But it can only be applied if the only non-linearity is just contact. So, and contact with no friction. So if let's say your model has non-linear material, you cannot use fast contact, okay? You can use fast contact if the only non-linearity is contact, right? Right, so non-linear geometry is not supported as well. That means large displacement also cannot be supported. Okay, so no large displacement, no non-linear material. If your only non-linearity is just contact and it doesn't have friction, then you can use fast contact, right? So fast contact is of course going to solve very much faster compared to the traditional or our traditional contact there, right? There are two ways to generate fast contact. You can either use fastcon, yes, or use this param CD iter, right? So this is going to use the MPC base. MPC is, imagine MPC like your RBE2. Okay, so this is the old NASTRAN approach, which we carry over from NASTRAN. You can also use param CD iter. There are two ways to that. Okay, so both will function the same. Sometimes you're gonna get convergence with fastcon, then maybe you're gonna try with this CD iter. Okay, that's only when you switch, right? But otherwise, you can use the fastcon, yes, and try to see whether you can get accurate results comparing to your traditional or the normal nonlinear contact. See whether you can get good results. Okay, so you have to set up as per node to surface. You can use surface to surface, only node to surface, right? And again with no friction. So here's an example of this fast contact here, right? So it's just normal CPU. These are the elements, right? And we compare the full nonlinear analysis with fastcon. Okay, so you can see fastcon. We have to look at the wall time. So fastcon just solved this in 18 minutes compared to 2.5 hours in normal nonlinear analysis. Okay, so yeah, it's going to solve very much faster, right? But again, only if your condition allows. Means that there's no other non-linearity, only contacts, and the contact is frictionless, right? So to activate that again, just to do this, right? You define your contact as per usual using the node to surface approach, and then you use a fastcon, yes. Right. Okay, so I'm gonna now jump into setting up contacts for this example here, right? Because we're going to use this later on and also apply pretension. So I'm going to show you how to apply pretension in the next chapter also. So this is the model that we're going to use for the next chapter as well. All right. So in the end, you should get something like this. Let's go into Hyperbox to set up this. Okay. So this is the model. Right. So what I did, let me just do this again. So I will import the file in. Before this, before we continue, any questions on the contact chapter? If you have any questions, you can just ask, just unmute and ask. I will also just continue on this demo for now, right? So for here, what we need to do is, this is the boat, of course, and it's gonna have contact in this area, right? So the boat is gonna be contacted to this yellow part, sorry, orange part, and also have contact with this blue part. And then between the orange and the blue part, we also have contacts, right? So what we can do now is to create those sets. There are some contacts already, but mainly this is contact for this gasket here. Okay, so you see they have contact here already for the gasket. So we only need to set up the contacts for the bolt area. Okay, bolt area doesn't have any contact yet. Okay, so to do that, let's just try this auto contact. I'm going to see how good it is. Okay, select my 3 components. The setting wise, I'll just leave it as default first because I can change it anytime. Okay, and just say fine. Okay, so we managed to search this contact. Okay, for the bottom, or you can say the nut, right? So this is good. I can accept this. Move to next contact. This is for the top, the bolt head. Right, I can accept this. Next. Oh, that's all. Okay, let's accept that first. Wait, let me see the rest. Oh, so he managed to create the other 2 was for the gasket. Okay, so he established contact for the top. So let me review this. Oh, sorry, this is for the bottom. So bottom, right? And for the top. Okay. Now let me double check on the surface created. Okay. Okay, so it generated that surface correctly. Just turn on the bolts, right? So this is for the nut area, and then this is for the top area. But for the top, it's the other way around. Right, so I need to switch this direction. This direction is okay, it's downwards. Okay, this one is upwards, right? So probably only this set here that I need to switch. So okay, let me isolate that, and I bring up my bolt. I just need to redefine this one here, right? So I need to use, before that, let me clear this up. Okay, and I will use, so it should always be outwards like this. So now the contact looks okay, right? Of course, you can go on and create contact for the shaft as well. Shaft and also for the components, right? Right, between here. Let me just hide one of it. You can see here, I should have contact here as well, but I'll just leave it for now. You can try it if you want. But I will define contact between the 2 plates here. Okay. So this one, it didn't manage to capture, maybe because I put it here, proximity to be 1.0. So if I measure here, it's actually 2 lah. So let's say if I now try, select the 2 components, put in a, let's say, let's put 2.5 proximity, and between the 2 components and find, it should be able to create that contact. Yep. So these are all the contact areas lah. Okay. So this is good enough. I don't need to do anything. So you can try auto contact. Otherwise, you need to manually create lah. Right click, create a surface, and then come to here, right click, create contact. Contact. Yep. So that's how you need to do it manually, and then assign your properties here. Okay. So for now, property wise, I'll just put them all as sliding first, see whether you get converged or not. Or surface to surface, so no problem. Tracking, I would use I think we can try small here, so you won't have any large displacement. Yeah, I'll just try with small. Then try to run this. Okay, so this is only the setting up of contact side. We haven't defined the pretension yet, and so on. So we'll do we'll do that later in the next chapter. Okay, so this is just defining contact. Of course, manually, if you want to define, you have to, go right-click, create a surface, and then right-click and create your contact. Okay, and then define your properties inside here. Okay, so auto contact now is good enough to handle this kind of situation. Just now I was talking about smooth here, so I couldn't see earlier because it was hidden. Now this is the smooth. If you need to have smoothing, just need to turn this to 1, or you can have 2. It depends on how many surface you have. Okay, you can have many as you want, because you can choose it to be smooth on the master side, we call it main, or the second side, which is the sleeve. So you can either choose smoothing on the main surface or on the second surface. Okay, choose for both. Okay, once you choose your side, you can also choose the region. So region means that maybe like here, like for my let's choose, go back to 0. Let's choose this one here. Okay, so let me bring them up. Sit. Okay, so let's say for this, for the purple and also the white contact, right, which is actually these two here. Supposed to be this one. Okay, this one. Okay, so for this and this contact, okay, now this better, right? For these two contact here, because even though they are just two ID, but they have different regions, right? So this is like the front region, this is the rear agent, the back region, right? So probably you want to have smoothing on just the front region and not the back region. Then you need to create different sets for them. Okay, I mean, now there's only one contact set. You need to define another area where you only apply smoothing. So let's say I'm going to apply smoothing on the front area only. So that's why you can have in the contact, you have this option here. First is the side, whether you want to smooth on which side. Let's say if you smooth both master and slave, top and bottom, then you need to choose the region as well. So you can either choose all the region, means both this region here will be smooth, or you can also select another set where you only have one region smooth. So in this you need to define another set that says only, maybe even for the front region, only I want to smooth at this area here. So you need to define another set for that. Okay. Otherwise, if you want to smooth the entire thing, just use all here. Right. So that's the smoothing that I missed out earlier. Okay. So when you're smoothing now, contact here is already set. So I will just save this for now, because I'm going to use it in the next chapter. Wait, let me see. Okay. So I have contact there. Let me talk a bit on the stabilize. So if you need to turn on the contact stabilize under Param Expert NL, you can turn this on, right? Contact stabilize, or you can control by creating a contact stabilize card as well. So you can go and right click here, create contact stabilize in the load collector. Okay, so this creates that contact stabilize card. Then you may want to edit these two values here. Factor of contact at the beginning and at the end. Okay, by default is we apply full contact stabilization energy at the beginning, and then at the end we put it at 0. Okay, but if at the end of your run you still find that something is still very hard to converge, then you probably want to add some very small value here. All right. So yeah, you can turn this on. Now we already have the expert NL. Expert NL is by default, so you cannot adjust the values there. But if you need to scale them, you can use this context stabilized cut. Otherwise, the param expert NL will handle that. All right. So I generally like to use param expert NL, let it handle itself. In the end, I just check the energy whether it's okay or not. Okay. Contact is on. Good. So yep, I think this is okay. Let's see what's running here. Okay. All right, so I cannot run this yet because I haven't set up anything. So this is only the contact that's set up. So I'll move on to the next chapter now. Any questions so far on contact definition? Okay, so if you follow the example, he's going to ask you to use a pcon. So it's the same thing. Let me just check what setting they use there. I can emulate it. So there is a pcon and they apply a friction of 0.2 plus separation, yes. So you can try this. I would probably not do separation, but I'll put that friction there. Okay. So I can update my contacts. Instead of going slide, I probably want to choose a friction coefficient and put 0.2 here. Okay. So it's similar to what we have in the pcon, right? Okay. The benefit of using pcon is you can create a property contact and then you can assign it to all three of them, right? So since we are here, I'll just show you an example as well. Let's say I create a pcon. I have that. Okay, stiffness, I just put it at auto first. Here I put 0.2 and separation, yes. So now this pcon is pcon ID 6. I can assign pcon to all of these as well. So property ID, assign it to pcon here. Okay, so I can do this also. I can select all of them. Okay, it doesn't allow me. Okay, so I'll just do property ID. I can do 6 here as well. So different ways of defining a contact. Depends on you. If you want to have a generalized contact for all your contacts, you can use pcon. Otherwise, you can go to each of the contact and then manipulate as well. Of course, you can also generate different pcons, right? Which has different friction, whether you can separate or not. So you can have different customization also. Okay. So you can try both, whether you use just the static friction or you're going to put pcon here. Okay. This. All right. Yeah, I guess that's all for contact. Okay, some best practice. Yeah, always try to use contact surface rather than using sets. So using the what we see here. Let me show you from here. Here, if you use the auto contact function, we automatically create set segments or surface here. Okay, so it's better to use surface instead of clicking create sets here. Okay, create set segments instead of sets. Right, if you use set segments, use the surface. It's going to be better for contacts. But you can also use sets and then use element set, or also grid set for node to surface. Okay, both the methods work, but we see better convergence with contact surface, right? Surface to surface should be used for large sliding. Okay. Here it suggests you to try constantly continuous sliding before going to finite. Okay, because it's more likely to converge. Of course, because it takes more, it's costlier, right? It's more expensive. So I normally will go the reverse. I try to use finite first. If you cannot solve, then I use continuous sliding. Okay, because I want to see my results fast. So yeah, so it's up to you whether you maybe like you don't have the time to experiment. You just go for continuous sliding, because it's more likely to converge. Okay, but if you have let's say if this run is gonna be like a benchmark for your future runs, so the future runs will also depend on what are the settings that are set here. Then probably you might want to, or if you have, or this is a initial run which you're going to improve, means you need to improve the design. You need to run a few iterations, a few design iterations. So you probably want to try to solve it with finite first, because finite is going to solve faster. And if finite works for this one, then probably the next one finite will also work. Okay, so that's where you can save some time there. Okay, but if you only have one of the runs, you just want to make sure that this is run by tomorrow morning, you can just try continuous sliding and let it run. So it's up to you whether which one you prefer. I would normally prefer finite first, because I want to try to get my run solved faster in the shortest time before I go to continuous sliding. Okay. If you have a contact surface that has a sharp corner, again, remember my example that earlier. Okay, if you have a sharp corner like this, right? This is slave, this is master. Then you two ways. Either you use node to surface, right? Which you then can define all your nodes here under one slave. Okay, and then here all of them under one master surface. Okay, if you use node. Okay, node to surface. If you use surface to surface, then there's a corner option which you can turn on. Okay, corner option which you can turn on. Or you split it into two surface to surface contacts. Okay, so I generally would prefer to split them, right? So that, like, if I split them, and let me see, right? This area here, I'm going to define as one contact surface. And then this area here will be another contact surface, okay? So the contact here can be turned on. It's going to be independent with the other side, right? So it can be on here, it can be off on the other side, and vice versa. So I would prefer this kind of setup where I split my contact into two separate contact surface. Okay. All right, so guys, something for you guys to ponder, and also do remember the rule of thumb, right? When you define your slave against master, slave is normally moving, softer, smaller, and also smaller mesh size. Okay. Again, slave is normally smaller in size, smaller in mesh size, is normally moving, and it's normally a softer material. Okay, so if you go by this, then your run should be okay. All right.